and welcome to the next video in my series on basic finite math. Now, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you have come pretty far in your schooling up to this point, you're smart, and you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can get through it. I have faith in you. Many others around you have faith in you, so should you. Number two, please feel free to follow me here on YouTube and or on Twitter. That way when I upload a new video, you know about it. And on the topic of the video, if you like it, please give it a thumbs up. Share it with classmates or colleagues, or put it on a playlist, because that does encourage me to keep making them. On the flip side, if you think there is something I can do better, please leave a constructive comment below the video, and I will try to take those ideas into account when I make new ones. And finally, just keep in mind that these videos are meant for people who are relatively new or brand new to finite math. So I will just be going over the very basic concepts. And I will be doing so in a slow, deliberate manner. Not only do I want you to understand what's going on, but also why. So all that being said, let's go ahead and get started. So this video is the next in our series on sets and counting. Usually this is one of the first things you do in the first few weeks of a finite math class. Now some universities do it differently, but where I was at Indiana University, this was one of the first things that was done in the first 2-3 weeks. So this video is about Venn diagrams. A lot of students freak out when they start working with Venn diagrams, even students who had AP Calculus in high school, because it requires you to think in a different way. But the reality is, we do this all the time in real life, whether we realize it or not. And maybe in this video, and definitely in the next video, I'm going to talk about how we actually create sets and subsets and intersections and unions and everything in our everyday lives without thinking that we're actually doing it. So let's go ahead and look at some problems. So just a quick review from our previous video about what sets and elements are. So remember, we have a set, and we're going to call this set N. Now you can think of the outside as kind of like a fence, so everything inside of it is part of set N. And in this case, it's the numbers 1 through 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9 are sort of inside our set N. Now we use the is an element of sign to denote things that are inside our set. For example, the number 4 is inside our set. It is an element of N, an element of set N. However, we also have the opposite. You can see that 12 up there in the right-hand corner, 12 is not a part of set N. It is outside of its boundary. Therefore, we say 12 is not an element of N. So it's the element symbol with a sort of slash through it. So those are just some very simple reviews of what sets are, what we call the things in them, which are elements, and how we denote things that are not part of a set. Now just a quick review about equivalent sets. So this set is actually 2 on top of each other. So I've kind of used a checkerboard pattern to try to show you that there are 2 sets here, but they are really sort of right on top of each other. Now the thing is, they have the same elements. So set N is 1, 2, 3, 4, 5, 6, 7, 8, 9, and so is set M. So N equals M, and M equals N, equivalent sets. Now in the previous video, we talked about subsets and proper subsets. Now in this case, equivalent sets are only subsets of each other. Okay, they cannot be proper subsets. So if you're not sure about that difference, please take a look at the previous video we did. But these are subsets of each other. So subsets and proper subsets. So here we have set N, and inside of it, we have nested this other set, E. Now, just by looking at the picture, you should be able to tell that E, all of it, the whole thing, is inside N. So think about this. Whatever is in N is everything in E in the gray part and everything outside of E in the orange part. That's N. So we say N is 1, 2, 3, 4, 5, 6, 7, 8, 9. But what about E? Well, E is just the numbers 2, 4, 6, and 8. So E is a subset of N. So we can write it like this. E is also a proper subset of N, which we write like this. Now, just a quick review as to why that is. See, it can be a proper subset because it's not equivalent. That's sort of the thing that, forbids equivalent sets from being proper subsets. So E is both a subset of N and a proper subset of N. And again, if you need to review those, just take a look at the previous video. So now talk about intersections. That's where these problems become interesting, and this is probably how your problems are set up in your class. So here we have N, and here we have E. So set N and set E. Now, if you notice, they overlap here in the middle. But the thing is that neither set is totally inside or nested inside the area of another. So there is no subset here. There will be some elements of N that will be outside of E. So if you look at the diagram here, everything that is in the pure orange color is only in N. Now there will be things that are in E but outside of N. So the part of the diagram that's just blue, those things are just in E. But what about the middle part, sort of the purple where the colors come together? Well, that is our intersection. And anything in that area belongs to both. It belongs to both sets. So let's take a look at that further. So let's say we have a set A, and it's the numbers 1 through 9. Then we have the set B, which are the numbers 6 through 14. So 1 through 9, and then 6 through 14. So the question is, what elements do these sets have in common? What elements do they share? Where do these two sets overlap? Well, if we look, they have 6, 7, 8, and 9 in common. Those are the elements they share. Now, if I write these sets so they actually overlap, so I line up the 6s, I line up the 7, line up the 8, line up the 9, what I can do is actually show where they overlap, where they have in common. So I can put a little graph there. So 6, 7, 8, and 9 are where they have their elements in common, where they overlap exactly. So 6, 7, 8, and 9 belong to both sets. The numbers 1, 2, 3, 4, and 5 only belong to A. So only in A. And the numbers 10, 11, 12, 13, 14 are only in B. So we have sort of three regions here. In the middle, we have the intersection. We have the overlap, the things in common, which are 6, 7, 8, and 9. Then we have numbers that are only in A, 1, 2, 3, 4, 5, and numbers that are only in B, 10, 11, 12, 13, and 14. Now, if we actually put this in a Venn diagram, it looks like this. So as you can see in the middle, we have 6, 7, 8, and 9. The area that's only A, sort of the very dark orange part, we have 1, 2, 3, 4, and 5, just like our graph above it. And then over on the right, we have the numbers 10, 11, 12, 13, and 14 just in the pure blue over there on the right. Now, we do have to make sure that our original sets are intact. So let's make sure we look at set A. So do we have the numbers 1 through 9? Well, we have 1, 2, 3, 4, 5 in the just A part, and then we have 6, 7, 8, and 9 in the overlap part. So if we kind of put our hand over the just blue part where B is, we can see that A does indeed have the numbers 1 through 9. Now check B. Does it have the numbers 6 through 14? Well, it has the numbers 10, 11, 12, 13, 14 in the just B part in the blue, and it has 6, 7, 8, 9 in the intersection. So if we put our hand over the orange part, and we just look at the intersection and the pure B part, we have the numbers 6, 7, 8, 9, 10, 11, 12, 13, 14. So again, we can look at it a couple different ways to show how this intersection is represented in just a general sort of graph up there in the upper right, or in the actual Venn diagram in the lower right. So a little bit more about intersections. What we say is these are the elements these two sets have in common. Now another way we can say it is that these elements must be in A and in B. In A and in B. So A is 1, 2, 3, 4, 5, 6, 7, 8, 9. B is 6, 7, 8, 9, 10, 11, 12, 13, 14. So what elements are in both? What do they have in common? So we say A intersect B, and remember that's the intersect symbol down there. It's over an upside down U. A intersect B equals the set 6, 7, 8, 9, or that intersection. And that's how we write that. So this is how we do very simple intersection using two sets that overlap and have elements in common. Now what about unions? So intersection is what they have in common. Union is a little bit different. Now the way we put this is that the elements in just A, they're in the orange, just B, they're in the pure blue, or both, and that's the intersection in the middle. So anything that's in just A, just B, or both. So we can also say the elements must be in A or B. Now in mathematics, we use the or as inclusive. So we really are saying they have to be in A or in B or both. So A is 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is this region right here. The A circle outlined in the green. B is this area. Now notice that down in the B set down there, I crossed out the 6, 7, 8, and 9. Well, why did I do that? Because when we're doing a union, we're interested in sort of what's in the whole thing. But we can't count those numbers twice. We're only going to count them once. So when we say, what is A union B? It's all the numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So all those numbers appear either in just A, just B, or both, or the elements are in A or B or both. And we don't double count the intersection where they overlap. Now in the next video, we're going to talk about cardinality. And that's where this comes into play when we can figure out what parts of our diagram we are missing. So just keep in mind that the union is basically anything that appears in that region once. And we just count that up, and that is our A union B. So if we really kind of take everything out, the numbers and the colors and everything like that, the union is basically this shape here. So depending on where you are in the world, you may or may not have what are called peanuts, but we have those here in the US. And this is kind of a peanut shape, or some people will call it like a bean shape. So we have what's in A, what's in B, or what's in both. If we kind of, again, erase all the lines, this is the sort of overall area we're interested in. Now, disjoint sets, there is no subset. Okay, there's no intersection. They're completely separate. So in this case, set N, intersect E, okay, is null. It's empty. So there is no intersection between N and E. And of course there's no subset because they don't overlap in any way. So these two sets have no elements in common because they do not overlap. And there are no subsets or anything because one is not inside the other. But remember, an empty set is a valid set. It's actually a very important set in many instances. But an empty set is a valid set. So you might get a question that says, what, and here's the diagram, and they go, well, what is N intersect E? And the answer isn't 0. The answer is not, does not exist. The answer is not whatever. The answer is empty. N intersect E is empty. It's an empty set. Now let's talk about the universal set. So basically the universal set contains all the elements we're interested in. And it really just depends on the problem. So you might have a problem that's about all the clothes in a store, or all the students in an academic program, or all the restaurants or other businesses in a certain region in the U.S. So the universal set kind of puts a boundary around all the things that will be under discussion or that we are interested in. And again, it really just depends on the problem. Now inside that universal set, we can have all kinds of subsets and intersections and unions and all kinds of stuff. So think about this. Everything that is in S, some of them are also in A here. So all of A is inside our universal set. There'll probably be some things in A and some things outside of A. So if an element is in S, but it is not in A, so it's sort of in the orange floating around outside there, then we call that the complement of A, which we denote with A prime. And we'll put numbers in here in a second. So everything in S can either be in A or not in A. Now there will be nothing outside of the universal set. So everything in the universal set has to be in either A or not in A. So let's look at this. Now look at our universal set. Look at all the numbers in that rectangle, including what's in A, because of course A is in S, so we have to count it. So that's the numbers 1, 2, 3, 4, 5, 6, 7, and 8. Now what is in A? Well, A alone are the numbers 2, 4, 6, and 8. And of course those also belong to S because it is inside S. Now the question is, what is A complement? What is in the universal set S but not in A? So A prime. Well, those are the numbers 1, 3, 5, and 7. So that's just, again, that's just the idea of the complement of a set. So whatever is in A is in there, of course, but there are still things outside of it in the universal set, so they are not in A. Now, of course, you'll have problems, and we'll do them in future videos, that involve the intersection of 3 sets. So this is a very common graphic you're going to be looking at doing all these Venn diagram problems. Now, I just kind of started to give you a hint of some of the things you're going to be finding. So if you look in the middle here, we have set A, B, and C. And right in the middle is where they all 3 overlap. So A intersect B intersect C. Now here are a couple bonus questions. What regions are A intersect B? So you have to be just careful. You have to develop a vision for doing this. So A intersect B. Let's look at A, the circle for A. Then we look at the circle for B. Now in what regions do they intersect? Well, one region they intersect is what we have labeled A intersect B intersect C. But there's also one more region where they intersect. You see it? Okay, that is the region to the upper left of A union B union C. So it's kind of a darker green color in the upper left. That's also part of A intersect B. So basically, what this becomes is like a puzzle that you have to solve. Venn diagrams where we have missing values and we're given certain values. We have to use set relations and set operations to sort of figure out the missing pieces of a puzzle. And I've always wondered why puzzle books don't have Venn diagrams in them, because that's exactly what they are. It's all about finding the missing pieces so all the parts add up to what we know they should be, what we have in the problem, etc. But we'll do these in future videos. Okay, so that's a very brief, straight to the point introduction on Venn diagrams. So again, we learned about intersections, we learned about unions, we learned about disjoint sets. We reviewed sets and subsets and things of that nature. So this is just meant to get you a firm foundation to do more complicated problems involving Venn diagrams. And trust me, they do get very complicated. They get very, logically, where we have all kinds of sets and parentheses and complements and crazy. So you'll see how they work. But the thing here is you have to develop a vision for looking at Venn diagrams. You have to think of them in pieces, sort of almost in layers. And sometimes many of the students I work with actually had to write out the pieces or separate out all the regions of the Venn diagram and then sort of put the pieces back together, one by one. And if that's what it takes, that's what it takes. That's completely fine. So again, it's just about developing a vision and sort of sense of how they work. Okay, so just a few reminders. If you're watching this because you were struggling in a class, I want you to stay positive and keep your chin up. You're a very smart, talented person. Some of this may be new to you, and it may just be temporarily, sort of challenging you, which is good. That's a good thing. Now, I know with the right amount of hard work, patience, and practice, you can get through it. Again, you should have faith in yourself, because me and other people around you at school and at home and everywhere else do have faith in you too, so you can do it. Please feel to follow me here on YouTube and or on Twitter, so when I upload a video, you know about it. If you like the video, please give it a thumbs up. And most important of all, just keep in mind that you are dedicated to be on here learning, trying to improve, and that's what matters. So, thank you very much for watching. I wish you the best of luck in your studies or in your business or whatever, and I look forward to seeing you again next time.